So, we have these two expressions, one for V, which is r dot r cap plus r theta dot theta cap, and we have another expression for A, which is r double dot minus r theta dot square r cap plus 2 r dot theta dot plus r theta double dot theta cap. So, we write those as components of velocity, radial and transverse component of velocity, and radial and transverse component of acceleration, and we just separate it out for future. We will just keep it here in this side for future reference. So, V r is equal to r dot, V theta is equal to r theta dot, okay. A r is equal to r double dot minus r theta dot square, A theta is equal to 2 r dot theta dot plus r theta double dot, okay. Now, what is interesting to note is that, let us assume that a particle which is moving in a circular orbit. If a particle moves in a circular orbit, then its radius is not changing, that means r dot is equal to 0. So, generally if we but immediately we see that r theta dot is also changing. If it is moving in a circular orbit, then theta is changing, so r theta dot is non-zero. So, although it is, there is a in this particular motion the radial velocity component is 0, we have a transverse velocity component and the overall velocity vector is a non-zero vector. Similarly, even if the acceleration due to one of, let us say for the same motion r double dot is not changing. So, we have a 0 here, but we still have a radial component of acceleration, and the angular component of acceleration is always there, because this term will be equal to 0 and this term will be non-zero. So, we see that for motion on a circular orbit, let us say if a particle is moving on this circle with a fixed radius r, the velocity will be v equal to r theta dot theta cap, and acceleration will be equal to minus r or capital R theta dot square r cap plus r theta double dot theta cap. Now, what is interesting to note here is, okay, there is no radial movement because it is always on this circular orbit. Now, if there is no radial movement, we immediately see that r component of velocity vanishes and we are left with only the theta component of velocity. But in acceleration, although there is no radial movement, we have a radial component of acceleration. And if we write theta dot, let us say theta dot, if we just write it as omega, we immediately see this acceleration we can write as a equal to minus r omega square r cap plus, sorry, this will be r omega dot theta cap, and this is nothing but the well known expression for the centrifugal acceleration. So, although the radius is not changing, there is no r movement, we have a r component of acceleration, which is very evident from this calculation, and also we are familiar with this because this is the this is the standard expression for centrifugal force. Fine. So, now let us look into the second component of theta, acceleration a little more carefully. We just take this. So, a theta is equal to 2 r dot theta dot plus r theta double dot, and this can be written as d dt of r square theta dot. If you compute this time derivative, the first term will be, I mean, if you just compute this and divide the whole thing by r, you will get back this expression. Okay. Now, velocity, look at this velocity component of along theta, it is r theta dot. Now, if this is your origin, if a particle has a velocity v, so it has two components in this particular representation. One component is Vr, one component is V theta, okay. And this V theta, which is given as r theta dot, is working in this particular direction, which is at a distance r from the origin. So, if we now want to calculate the angular momentum L, which is given as r cross p, will be m r square theta dot. Okay. Now, which will this will have a magnitude of m r square theta dot, and we simply call this L. So, this can be rewritten in terms of 1 by r d dt of, or we put an m here, m r square theta dot, which will be written as 1 by m r L dot. Okay. Oh, sorry, it is not visible in this. So, we will just write this as 1 by m r L dot. Okay. So, we see that the angular component or the transverse component of acceleration can also be written equally well in terms of the angular momentum, the magnitude of the angular momentum, okay. And of course, it is pointing in the direction of theta dot, theta cap. Fine. Now, let us try to write the expression for, so we will just keep it here. So, we will just write L dot by m r and remove this. Now, a central force, which is a force always either along or away from a fixed point at a distance r. So, it is either pointing towards the fixed point or moving away from the fixed point, and if you remember, the magnitude of the force is a function of r only, that is the property of central force. There cannot be any theta dependence, there cannot be any other dependence except from the except for dependence on the distance of this force. Now, we are not talking about the general nature of the force law, it could be, I mean, so sorry, right now we are discussing the general nature of the force law, we are not talking about any specific force component. So, F r can be written as F r r cap. Does not matter whether it is an attractive force or a repulsive force, it has a magnitude which depends on this distance r only, and it has a direction which is either pointing towards the fixed point O or moving away from the fixed point O. Irrespective, this is the standard notation we use for central forces. Now, if this is the nature of the force, then once again we try to write the torque. Okay. So, we have Newton's law as F equal to m dv dt, or more fundamentally, as we discussed in one of our previous classes, d dt of p. So, this is from Newton's second law. and we immediately see the immediate conclusion is if f is equal to 0, p is equal to constant. We can write a similar relation in terms of angular momentum. We just have to replace this left hand side with n, and that, okay, let us do it actually systematically. N is equal to r cross f, it is the torque of f at origin. Okay. Torque of this force F at origin is given as N. Now, if we take dN dt, which will be d dt of r cross F, okay, and there is a relation that says dN dt is equal to, and there is a relation that says n is equal to d dt of L, L being the angular momentum, which is defined as r cross p, p being the linear momentum. Okay. So, if we have torque equal to 0, we immediately see L is a constant, and let us do one more step and we will immediately realize that n has to be equal to 0. R cross p is equal to r dot cross p plus r cross p dot. Now, please remember p is equal to mv, assuming that the mass of the system is not changing. Please remember, we are now please understand this, we are back into the systems, we are in the description where mass is a constant. So, there is no time derivative for the mass term here. So, angular momentum m, the linear momentum p dot is nothing but this is v, this is mv, this is r cross m v dot. So, there is no time variation of mass. Now, v cross v will always give you 0, okay, and we have r cross r cross, now m v dot is p dot, which is f external. Actually, we do not have to write this step, we can simply write this as p dot and this is r cross. Now, using this form, which is once again equal to 0. Okay. So, the right hand side of this equation will always vanish, which essentially means the time derivative of this angular momentum will always vanish for a central force, because we have this particular form of the force which is along r. So, r cross r cap will always give you 0, right. So, that is from the basic vector calculus. So, curl of cross product of two vectors pointing in the same direction will always vanish. So, if that is the case, we immediately see that for a central force field d dt of L is always equal to 0, which essentially means L is equal to a constant. And this is a vector equation, d dt of, so here we are computing d dt of L, which is r cross p, and that gives us L is a constant. Does not matter what is the particular form of this function f of r, does not matter because it is pointing only towards r. Because of this particular form of central force, L will always come out as a constant. So, this is a very, very, very important result which essentially tells us that the angular momentum of a particle moving under the influence of a central force is is constant. Now, there is a very special case where L can also be equal to 0, because L is given as r cross p, which is m times r cross v. Okay. Now, if for a particular case for a particular type of motion r and v is in the same direction, then this term will also vanish. This term will vanish and we will have L equal to 0 if and only if r is parallel to v. Now, that happens when we have simple harmonic motion or simple harmonic oscillation, if you want to call it. What happens in a simple harmonic oscillation in 1D? We have a particle which is, let us say this is our force center O, and a particle which is moving along this line like this. So, r is along measured measured along this length or this length, and v is also in this range. So, r and v are always parallel. So, we get a special case of simple harmonic oscillation where L is equal to not only a constant, but it is always equal to 0. So, that is a special case. So, in general, if we have a motion under central force, that means L is equal to constant. Now, this L being constant immediately tells us that the motion is also a planar motion. How? Okay. L is equal to r cross p, right. So, let us say we have the vector r is the position vector and p is the momentum at any given point. Now, L being constant, that essentially means that it is not only the magnitude of the vector L, as I have discussed already in this class, that it is not only the magnitude of the vector, but also the direction towards which it is pointing is a fixed direction in space. Now, if you examine this term, p is the momentum, linear momentum of this particle which is moving under the action of central force, and r is the radial vector which connects that to the origin. Now, if and only if r and p lie in the same plane, let us assume this situation. It is a some locus of the particle. Okay. So, this is your r, and at any given moment the velocity vector is pointing towards the tangent of this locus. Okay. Now, r cross v, so r cross p essentially means m times r cross v. Okay. So, r cross v, if it has to have a fixed direction, it is necessary that r and v they lie in the same plane. If not, the magnitude might remain the same, but if it is not in the same plane, the direction of r cross v has to vary. Now, if they stay in the same plane, then r cross v has a direction in this particular case which is pointing inside this plane. If v is, let us say, if the particle is moving from this direction to the, in this way, so v will be like this, and r cross v will be pointing outward of this plane. But irrespective, L is either out of the plane or inside this plane, and if that direction has to maintain, r and v has to be on this particular plane of the board in this case. If they are somehow living out of this plane, the direction of L will also change. So, we see that as R is given L is given by R cross V, L equal to constant means R and V has to be in the same plane. So, that essentially means the motion has to be a planar motion. Okay. So, we immediately see that the two properties of central force, which is namely motion in a plane and L being a constant vector, is immediate conclusion of F being having this particular form F r times r cap. Okay. So, these three are essentially related to each other, and also the last property or the third property which I also stated, that is an energy conservation. We will see that because these central forces F r, I mean there is a, these are all conservative forces by nature and there is a potential function associated with it, it is obvious that the energy will be conserved in this. So, we essentially proved all the properties of central forces. Now, let us try to look at the equation of motion. But before that, we also need to prove another very important aspect of, okay, let's first do the equation of motion, then we will come back to this. Okay. Okay, so equation of motion is ma equal to f of r, which is f r cap. So, if we go by the component form, we immediately see we have two equations, which is r double dot minus r theta dot square, which is a r equal to f r r cap. Or so, r cap is not needed because we are writing the component equation, and a theta equal to 2 r dot theta dot plus r theta double dot, which can be written as 1 by m r ddt of L. We already proved that L is equal to constant, that so no surprise that this whole thing is equal to 0. So, even this equation itself implies that L is a constant, because a theta essentially we have seen that it can be written as 1 by m r ddt of L. Sorry, there is no vector here. So, this essentially tells us L is a constant. But please remember that this L is a magnitude only. So, it only give, so this particular equation, if we consider that ddt of L is equal to 0, it only gives us half of the information. The complete information lies here, where we say not only the magnitude, but also the vector is equal to constant. Okay. Fine. But now, if we try to solve these two sets of equation, okay, this equation essentially does not give us anything new, because it only tells us that the magnitude of L equal to constant, which is also a basic property of the central force, which we know already. So, we will just leave this from the question. Now, if we try to solve this equation, we have a second order differential equation in theta and first order differential in second order differential in r and first order equation in theta, first order differential in theta. It is extremely difficult to solve in this particular form. What we can do is, we can try to write the total energy, which is a constant, as a sum of kinetic energy plus potential energy, and kinetic energy will be half m v square is r dot square plus r square theta dot square, okay, plus potential energy is V of r, where V of r is the potential function which is given as integration f dot dr from infinity to r. So, potential by definition is the work done from bringing this particle in question from infinite distance to a distance r, that will give you the potential at a point r. Okay. So, this is a Vr. Assuming that we know that functional form of Fr, we also have a knowledge of Vr. Okay. And this whole thing is a constant, because E is a constant. Now, if we slightly rearrange this equation here, and please keep in mind that L is equal to m r square theta dot is also a constant. Okay. Now, if we rearrange this bit, what do we see? We can immediately see that r dot square is equal to 2 by m theta dot square. Oh, sorry. 2 by m E minus Vr minus r square theta dot square, and if we substitute theta dot is equal to L by m r square from this relation, we see that r dot is equal to root over 2 by m E minus Vr minus, I will just give you the final form, L square by 2 m r square whole to the power half. So, we have one equation for r dot and one equation for theta dot. So, in principle, we can first, in principle, again I am not asking you to do it, or I am not doing it myself either. We can integrate this equation, because this is E is a constant, Vr is a function which we know from this relation, okay. L is a constant. So, we have a right hand side which is a function of r only, and in left hand side we have dr dt. So, we can integrate this equation to get r as r of t, then we can put it back in here, and we can integrate this equation to have theta as. So, this equation will give us theta as theta of t, and the trajectory is solved. So, what we need to know? In order to solve the equation of motion, we need to know the total knowledge of r and theta in terms of time, right. So, if we can integrate this equation and this equation one after the other in order to get r as r of theta and theta as r as a function of t and theta as a function of t, we essentially solve the problem completely. But as you can guess by looking at this this particular form, maybe under certain circumstances this integration is easy to solve, but in general it is a very complicated equation to solve, and then we have to get not only this, we have to get the functional form of r, plug it back in here, and we have to solve for theta. So, it might be easy when we have a computer simulation. I mean, when we are running a computer simulation, that might be an easy way, but at least at this level, when we are trying to solve problems in the classroom and trying to get an insight of the things, this form is not the best form of equation, say equation of forces we can have for central forces. So, in the next class, what we are going to do is, we are going to develop or rather we will start with this existing equations, and we will try to modify it in a smart way, so that we can get something which is more easily understandable and more easily solvable.